Alright everyone, welcome back to week 4 of our videos. So last time we were doing our first uh, video on undoing derivatives. This one we're going to do about talking about areas under curves. The next video will be the last video for all the things we need to do to cover our Calc 1 material, and then I'll do 2 more videos next week, which will be introductions to things you'll see in Calc 2. Okay, so before we can talk about areas under curves, I need to introduce a little notation. So in grade 2 or grade 3, we can come up with a notation for adding the same thing up a few times. So for example, if we want to add 3 up 4 times, we could write as 3 plus 3 plus 3 plus 3, or we could write as 4 times 3. And the same if you wanted to add 3 up 100 times, you could write down 3 plus 3 plus 3 and so on 100 times, but that's where multiplication becomes really useful because you can compact all of that addition down into one nice notation. And that works great so long as you're adding up the same thing. But then we might say, well, what if we're adding up kind of related things? And that's where this sigma notation comes in. So the sigma notation just means that we're going to take a sum from k equals 1 to n of each of these AKs. So we'll just add up a1 plus a2 plus a3, and so on up to an. So for example, we could write a sum, we could write 3 plus 3 plus 3 plus 3 using sigma notation. So we could write as a sum from k equals 1 to 4 of 3. So we would take a1 to be 3, a2 to be 3, a3 to be 3, and a4 to be 3. So we would then sum up 3 plus 3 plus 3 plus 3, and we'd get 12 as we'd expect. And if we wanted to change this to be a sum to add up 300 times, we'll just take the sum k equals 1 to 100 of 3. But there is no requirement that we keep everything the same. So for example, we could take the sum from k equals 1 to 4 of k. So when k equals 1, we have 1. When k equals 2, we have 2. When k equals 3, we have 3. And when k equals 4, we have 4. So we add up 1 plus 2 plus 3 plus 4, and we get 10. We could also take a sum from k equals 1 to 3 of 1 plus k squared. So when k is 1, we get 1 plus 1 squared. When k is 2, we get 1 plus 2 squared. And when k is 3, we get 1 plus 3 squared. We add all that up, we get 26. Or we could take a sum from k equals 0 to 4 of sine of k pi over 2. When we do that, we'll get sine of 0 plus sine of pi over 2 plus sine of pi plus sine of 3 pi over 2 plus sine of 4 pi over 2. We add all that up, we get 0 plus 1 plus 0 plus minus 1 plus 0, which is 0. Okay, so a couple of rules. Mostly this isn't necessarily that important for what we're going to do. I just don't want to pull all this stuff out of the ether. You see more of these when you get to Calc 2. So this is kind of a very brief introduction to sigma notation and sums. So a couple of things we can do. As kind of we might expect, with constants, we can factor a constant out in front. And if we have a sum of sums, so we have a sum of AK plus BKs, we can split that as a sum of the AKs plus a sum of the BKs. Now there are a couple of canonical formulas that are given for kind of special sums. Again, you don't need to know these at all. I'm just going to make use of one of them later, so I just want to make mention of these. You'll see more of these in Calc 2. So the first one that we have is a sum of constants, and that's just the constant times the number of terms you're going to have. We have a sum from k equals 1 to n of just regular k, and that is n times n plus 1 over 2. And then we have these other two sums, so a sum for k squared and a sum for k cubed. Again, you don't necessarily need to know these, but I'm going to refer back to one of them, so I figured I'd mention these here. Okay, so we want to talk about how we'd find areas under curves. Well, let's start with a basic example. So let's start with just the function 3 from 0 to 2. We want to find how much area is underneath our function and above the x-axis. Well, what we have is just a rectangular region. We have a height of 3, we have a base of 2, so we could easily say that there are 6 units of area here. Okay, that works great. What about this next region? Well, we want to find the area of this gray region, and what we could do is we could break this up into three smaller regions. So we could say this first region we have a height of 3 going from 0 to 2, so we have a rectangle there. In between 2 and 3 we have a trapezoid, so a we'd have two bases. We'd have this height of 3 and then this height of 4, and then we'd have or I guess we'd have a base of 3 and a base of 4. And then the height of our trapezoid is going to be 1, so the difference between 2 and 3. So we'd come up with the area there. And then our third region, we have another rectangle, so we could find the area for that region, add each of these three up, and that'll give us the total area in the gray shaded region. Okay, great. Well, what about the function t squared plus 1? Well, we don't have a nice geometric shape. We don't have a rectangle, we don't have a trapezoid, we don't have something like that. But what we could do to start is maybe we can't find the exact answer to this, but we could approximate it. Right? So instead of trying to come up with something exact for this gray region, we'll take a couple of rectangles and we'll try and approximate the region. So what I mean by that is I'm going to, in this case, try and approximate this total gray region with the area of a couple of rectangles. So what I'm going to do is I'm going to split my interval from 0 to 1 into two different smaller regions, 0 to a half, 1/2 to 1, and then I'm going to come up with heights for the rectangle and use that to approximate the area of the whole region. So here we have is I have one rectangle with width 1/2 and height 1, then I have another one with width 1/2 and height 5/4. And to get my approximate area, I can just add the area of these two rectangles. So I have 1/2 times 1 plus 1/2 times 5/4, which is 9/8. But what we see is that we have a bit of an under approximation. So the actual area is going to be a little bit more because we're missing some area in between here, and then we're also missing out on a lot of area there. Well, okay, maybe I take a couple of rectangles, but I take different heights. So now what I'm going to do is I'm going to pick one rectangle to have height 5/4, the other one to have height 2, add up the area from those two rectangles. And when I do that, I get 13/8. But here we see we're going to have an overestimate because we're going to pick up a little bit too much area here. And then we're also going to pick up too much area over here around kind of the 1/2 0.6 region. Okay, well I could pick two more rectangles, pick some different heights. So now what I'm going to do is I'm going to pick the point where I'm going to use for the height of my rectangle. I'm going to put it in the middle. So I'm going to take f of 1/4 and f of 3/4. And when I do that, we get something that looks like a better approximation. We're picking up a little bit of area over here around 0. We're losing some area closer to on the left side of 1/2. We're picking up some area on the right side of 1/2, and we're losing some area around 1. So what we've still got something that's maybe not quite correct. We're probably losing a little bit too much area because it looks like the area that we're picking up over on the left side at 1/2 is going to be more than the area that we're picking up around 0. Same kind of things happening around 1 and the right side of 1/2. So we've probably got another underestimate, but this one looks better than the other two. But again, we had rectangles with width 1/2, height in this case 17/16, and then the other one is height 25/16. We add up those two areas, we get 21/16. So maybe we're not happy with this approximation, maybe we'd like something better. Well, what we could do to get something better is just take more rectangles. As we take more and more rectangles, what we see is that the approximation that we're going to get is going to increasingly get better as the number of rectangles grows. And what we see here is that there are tiny slivers of area that are either being picked up or discarded. And over as we're closer to 0, there's an imperceptible amount of area that's being picked up or discarded. So we could try and do something like this. Okay, so first we're going to define just a couple of terms. So the first is that we're going to say that we have some interval a to b. We're going to divide it into a regular partition if we divide it into n subintervals of equal length. So what we just did was a regular partition of two subintervals. We divide the intervals 0 to 1 into the intervals 0 to a half, 1/2 to 1. So here we would have subintervals x0 to x1, x1 to x2, and so on. The length of these subintervals is just going to be given by the size of the interval divided by the number of subintervals. So for us, that would have been 1 minus 0 over 2. Our intervals had length 1/2. And then if you wanted, you could come up with an explicit writing for what we'll call these grid points. So these are just the points where you're dividing the subintervals. So what we just did, we had our subintervals went from 0 to 1/2, 1/2 to 1. So our grid points we would say would have been 0, 1, and, or sorry, 0, 1/2, and 1. Okay, so the general idea for how we want to approximate this is we'll divide up our interval into some subintervals, and we'll pick some point inside each interval, and we'll make a height for each rectangle in the subintervals given by f of this xk star, where the xk star is the point that you picked inside the subinterval, and the base of the rectangle has length b, which is the size of the subinterval. So we have what are called Riemann or Riemann sums, depending on how you want to pronounce the German. And you can approximate the area underneath some function just by adding up the areas of all these rectangles. So we would add up the height of the first rectangle times the width of our rectangle. And then we would add up the height of the second rectangle times the width of that second rectangle, and so on. And then there are three kind of canonical ways that we would go and choose the heights for the rectangles. So one is by using the left points, the right points, and the midpoints. So that's what those three examples were. The first one where we picked the points 0 and 1/2 to give us the heights for the rectangles, that was using left points. When we were using right points, we took the points 1/2 and 1 to give us heights for the rectangles. And then the third example, which gave us the best approximation that we had there, was using the midpoints of our intervals. So we had the interval 0 to 1/2, so we picked the midpoint of a quarter. And we had the interval 1/2 to 1, so we picked the midpoint of 3/4. Okay, so we could go and do this again, and we could go and take now 4 rectangles. So we'll go and split the interval 0 to 1 up into the intervals 0 to a quarter to a half to 3/4, and 3/4 to 1. If we use left points, we'll be using the points 1, 1/4, 1/2, and 3/4 to get heights for rectangles. When we add up the areas of all of these three rectangles, we get 39 halves, which is about 1.22. We could again go and do right points. So we'll take the points a quarter, a half, 3/4, and 1 to go and get heights for the rectangles. We'll add up the areas of these 4 rectangles here and get 47 32nds. And again here what we can see is, yeah, we'll have an overestimate because we're picking up a lot of extra area. And if we wanted, we could also do midpoints. So we'll take the middle of the 0 to 1/4 interval, which is 1/8, the middle of the 1/4 to 1/2, which is 3/8, the middle of the 1/2 to 3/4 interval, so 5/8, and then lastly 7/8 is the midpoint of the 3/4 to 1 interval. And when we go and we add up all of the areas of these rectangles, we get 85/64, which is about 1.33. And if 4 rectangles wasn't good enough for you, you could go and say take 20, as I have here. If you took the left point approximation using 20 rectangles, you'd get 1047 over 800, which is about 1.3. If you took the right points, you'd get 1087 over 800, which is about 1.35, 1.36, something like that. And lastly, if you took the midpoint with 20 rectangles, you'd get 2133 over 1600, which is about 1 1/3, a little bit less than 1 1/3. Okay, so what we're seeing with this is that we take more and more rectangles, our approximation gets better and better. And this maybe isn't surprising, and we can formalize it with this next result. So the exact area under a curve is given by taking the limit as n goes to infinity of the number of rectangles. So what you're going to do is you're going to take the rectangles to be increasingly thinner, and you're going to sum up an increasingly larger number of rectangles. So sum up an infinite number of infinitesimally thin rectangles, and that is your exact area under the curve. Okay, so we're going to do one example with this. I kind of do this more for completeness than anything else. For tests and such, you're not going to be asked to find the exact area under for some function. You'd be asked to do an approximation. So you'd be asked to do a left point or a right point approximation with typically 4, maybe 5 rectangles, so the kind of examples that we just did. But this is, it's kind of informative to go and see how this actually works. And you probably see this again in Calc 2, so may as well see it now. Okay, so what I'm going to do for simplicity is I'm going to go and choose the right point rule. So I'm going to define my xk stars. This is supposed to be xk, not xk minus 1, my mistake. So I'm going to define my right points so that I choose my xk stars to be a plus k delta x, where for us, we're going to take the delta x to be the size of the interval divided by the number of rectangles, so 2 over n. So that tells us that xk star is going to be 2k divided by n. Okay, so we first go and set up our equation. The area is equal to the limit as n goes to infinity of the sum from k equals 1 to n of f of xk star times delta x, where our xk star is in between xk minus 1 and xk. For us, for the things defined, that'll give us a limit as n goes to infinity of the sum of k going from 1 to n of f of 2k over n divided by 2n. Our function is x squared, so we're going to take our argument, 2k over n, and square it. And then we still have that 2n. And when we expand things, we'll get that a is going to be the limit as n goes to infinity of the sum of k going from 1 to n of 8k squared over n cubed. Okay, so now what we're going to do, we're going to pull out some constants. So 8 is a constant with respect to our sum and also our limit, so we can just pull the 8 all the way out to the front. Now for the sum is ranging over k, so k is the thing that is changing. When we fix an n is constant with respect to our sum, so we can just pull that out in front. So we can rewrite our area expression as 8 times the limit as n goes to infinity of 1 over n cubed times the sum from k going from 1 to n of k squared. And now this is where I'm referring back to the closed forms for special sums that I had at the very beginning. And the sum from of k squared, k going from 1 to n, is found to be n times n plus 1 times 2n plus 1, all divided by 6. Where this comes from isn't important, but we'll just take it as magic for now. Okay, so we've now evaluated the sum, we just need to evaluate the limit. So we can put the 6 out in front and make it a 4/3. And we now have that our area is going to be 4/3 times the limit as n goes to infinity of the polynomial of this rational function. So expanding this out, we get a numerator of 2n cubed plus 3n squared plus n, and then our denominator is still n cubed. So we're looking at a limit as n goes to infinity. We have a rational function, so we know that we can just compare the highest order terms. The highest order term we see in the numerator is 2n cubed. Highest order term we see in the denominator is n cubed. So that tells us that the limit is going to be 2, and then the entire area is going to be 8/3. Okay, so that gives us an idea of all the work that we would need to do to find the exact area. It's maybe more work than we'd like to do, so we'll kind of see what we can do to simplify that out a little bit. Okay, the next thing that we could ask, well, so far what we've assumed is that our function is always positive. What happens if we look at something like sine of x, where it's not always positive anymore? Well, we could do the same kind of thing, just so long as we allow heights to now be negative. Maybe kind of strange, but mathematically it's totally coherent. So here what we'll do is we'll take sine of x and we'll approximate it by 15 rectangles. So I have the ones from 0 until pi. They're all going to have positive heights, but then these rectangles from pi to 2 pi are going to have negative heights. So what we'll say with these is that if you give me some region R it's bounded by the plot of the function f and also the x-axis in between a couple of points, we can talk about what's called the net area. So the net area is just going to be summing up all of the area that lies above the x-axis, and then we're going to subtract off the area of the parts lying below the x-axis. So to analogize this, so in football, you might look at a punter's net average on punts. So the net average on punts is just the total distance that the punter punts the ball minus any return yardage. So for example, if a punter is starting at midfield and he punts the ball 50 yards, well, the ball goes into the end zone for a touchback. The other team starts with the ball at the 20. So the net yardage on that punt is the 50 yards for the punt minus the 20 yards back for the touchback. Similarly, if the punter punted the ball, say, 55 yards and the other team returned it 10 yards, the net yardage is 45 yards. So 55 for the punt minus the 10 yards on the return. And that's kind of what we're doing with net area. Okay, so what we would do here is we would sum up the green areas and subtract off the red one. Right, and then doing our rectangle approximation, we would just add up the approximation. We'd add up the areas for the green rectangles, subtract away the areas for the red rectangles, or I guess depending on how you want to frame it with negative heights, add areas, add the negative area. Again, depending on what point of reference you want to use. Again, with this, we could always go and take more and more rectangles, and as we take more and more rectangles, we'll get a better and better approximation. So the same kind of idea will hold. If we take a Riemann sum with n approximating rectangles, we'll have the same thing, and we'll just now allow our f's to be negative. So we'll allow the heights of all these rectangles to possibly be negative. And what we'll do is we'll use this notation. So last time we used this elongated s to denote an antiderivative, but it didn't have these numbers on it. So we're just going to use the elongated s with numbers on it to mean something different. So here we're going to use it to mean is the exact area under the function f from x going between a and b. Okay, so if you give me a function that is either continuous or it's bounded and has a finite number of discontinuities, then we can always find something like this. So we could find this limit as n went off to infinity of the sum from k equals 1 to n of our f of xk stars times our delta xk. The other thing we could do if we really wanted to is we could allow the sides of the intervals to vary if we so chose, because why not? Okay, so we could go and find some areas of regions for nice geometric shapes. So for example, if we take the function 2x minus 6, we could go and find the exact area for that using kind of nice geometric results. So we could do this in two ways. So one is we could say, well, we have on the left-hand side, we have a triangle. On the right-hand side, we also have a triangle. The area on our left-hand side is going to give us something negative. The area on the right side will be something positive. So we'll just find the area on the right, subtract away the area on the left. And that'll totally work. We'll see that it'll totally work. The other thing we could do is we could say, well, we have a trapezoid. Just one of our heights is negative. And again, we'll do that and we'll see that we get the same answer. So the first thing we could do is we could say we have one triangle, it has base 2, the height is minus 4, the total area, base times height over 2, is minus 4. The second triangle has base 3, height 6, the area is base times height over 2 for 9. We add up our areas, we get 9 minus 4 for 5. The second thing, as I said, we could do is we could say, well, we have a trapezoid. So our base is going to be 5, one of our heights is 6, the other height is minus 4. The area for a trapezoid is given by base times height 1 plus height 2, all divided by 2, and again, that's 5. Okay, the second thing we could do, we could take the function 2x plus 3 and go from 2 to 4. Well, if we do that, if you really wanted, you, I guess, could divide this up as a rectangle and a triangle, but I think I'm just going to do this as a trapezoid because it's kind of easier. So here what we'll say is, well, we were going from 2 to 4, so our base is going to be 2. The height at 2 is 7. The height over here at 4 is 11. So we'll take these three values, put them into our area expression for trapezoids, and get 18. Okay, so we can find areas for triangles or trapezoids, but then we could also look at a function which looks kind of strange, the square root of 1 minus the quantity x minus 3 all squared. The function, as I said, maybe is not obvious what it's looking at, but if you look at the plot of this, it's quite clear what we're looking at. We're looking at a half circle of radius 1 centered at 3. So we want to find the area of a circle. Our radius is 1, and it's, in this case, a half circle, so we'll get our pi r squared over 2, or pi over 2. Okay, so that tells us kind of some nice ways that we can find exact areas under curves, and then we have a couple of kind of rules for definite integrals. So the area between a and a is 0. Think about that as you have the area of a rectangle of width 0. It's 0. The area from a to b of f of x is equal to minus the area from b to a of f of x. So what this on the right would be saying is, so instead of going from left to right, you go from right to left. Now what you would be doing when you go from right to left is you'd be negating all of the widths of your rectangles. And if you negate all of the widths of the rectangles, that's where this negative sign is going to come from. If we wanted to find the area from a to b of some function f plus g, we could find the area from a to b of f and add it to the area from a to b of g. If you want to find the area from a to b of some constant times our function, you could go and find take the constant multiplied by the area from a to b of f. And we can also split intervals up. So we could go and find the area from a to b of a function f by finding the area from a to c of f, and then the area from c to b. And then lastly, this one's not overly important for us, but if it turns out that the absolute value of some function is integrable, so we can find the area from, we can find the area underneath the absolute value from a to b, then the the area from a to b of the absolute value of f of x is going to give the sum of the areas bounded by f and the x-axis. So what this would do is give us the total area. So when we had the net area before, this absolute value part would just give us the total area added up. So we just take the absolute value of each of the pieces. Okay, so then something else that we could do is we could take this function x cubed, and we could go and try and find the area of this gray shaded region. Now, if we really, really wanted to find this exactly, so far we would have to go and use the limit as n went to infinity of a sum of rectangles. I'm going to kind of skip over that because it's very much the same as the example before, but I'm just going to kind of sketch a little bit about this. So what we could do is, instead of finding the whole thing, I'm just going to mention a couple of pieces. So if we wanted to find the area between -1 and -1/2 of x cubed, it would look like this. So we'd have the area of this gray shaded region. We could do the same thing from -1 to 0. We could then do the region from -1 to 1, and lastly the region -1 to 2. Okay, so we can define what's called this area function. So we'll fix a left endpoint, and we'll say that the area function for some point x, where x is going to be to the right of our point A, will be found by just the area between a and x of our function, or the net area between a and x of our function. So for the example that we just had, x cubed, if you wanted to find the area between -1 and 1, as we said, that's 0. If you want to find the area between -1 and -1/2, turns out to be -15 by 64. The area from -1 to 0 is -1/4. The area from -1 to 1 is 0. And the area from -1 to 2 is 15/4. Okay, so we could go and find the area function for example this trapezoid that we had from before. So we had the function f of x was 2x plus 3 going from 2 to 4. Let's try and find the area function for that. So we'll fix our left point at 2 and go from there. So our base is going to be x minus 2. The minus 2 coming because we're starting, we're fixing our point at x is 2, and our area function is going to give us some point to the right of that. So for example, when we were looking at the trapezoid going between 2 and 4, the base was 2, or 4 minus 2. One of the heights that we're going to have is going to be the height at 2, which we said was 7, and the height at some other point x is 2x plus 3. So we'll take these three quantities and put them into our area equation for the trapezoid, and after reducing it down, we'll get that the area function is going to be x squared plus 3x minus 10. So we can just make a couple of checks to make sure that we got the right thing. So we know that the area function at 2 had better be 0, and conveniently we get 0. We get 4 plus 6 minus 10, which is 0. And then we said that from before, the area for this trapezoid going between 2 and 4 was 18. If we evaluate this area function at 4, we get 18. So we've got the right function. Okay, so now we want to transition a little bit and talk about what is called the fundamental theorem of calculus. So you know this is important because it has the word fundamental theorem in it. Okay, so what we've said so far is that we can find an approximation for the area underneath some curve by going and using a bunch of rectangles. So for example, I'm going to take this function f of t and go from the point 1 to some point x. But then what I could do is I could go and extend, we'll cut this out. Okay, so what we have here, so what we've said so far is that we can approximate the area underneath some function by going and taking a lot of rectangles. So here we have is some function, and I'm approximating with rectangles, and we're going from 1 up to some point x. But then what we could do is we could say, well, what if we went and stretch things out a little bit farther? So instead of going from 1 to x, we go from 1 to x plus some other value h. So what we'd see between these two images is that I've added on this rectangle on the right. Okay, well, the difference between the area function evaluating at x plus h, so this right point here, which is in line with 2, and where we were before, so over here, just a little bit to the left of 2, it's approximately h f of x, where h f of x is going to be this area that's in orange. So f of x is right here, and the h was the width of this rectangle. Okay, well, we could go and do something that's kind of straightforward. Let's divide both sides by h. Maybe not for any apparent reason, but let's just do it. So what this says is that the difference in the areas divided by h is approximately equal to the height here. Okay, now we're going to do something that seems even less obvious. We're going to now take a limit as h goes to 0. So what this is doing now is it's saying as the width of our rectangle gets really, really thin, the difference in the areas that we had divided by the width of our rectangle is going to be equal exactly to the height of this rectangle. So what's going on here is we're saying we're going to make the width of this orange rectangle be very, very, very thin. And then the area of that orange part, or sorry, the ratio between the area of this orange rectangle, this now very thin rectangle, and its width is the height of the rectangle, so f of x. But then this expression that we have on the left-hand side of the equal sign, that is just our definition of a derivative for the area function. We have the limit as h is going to 0 of some f of x plus h minus f of x, all divided by h. That's a prime of x. And that leads us to what is called this fundamental theorem of calculus. So we'll define the area function as we had before. So it's the definite area, or sorry, the area, the net area underneath the function f. Here I'm using t just because I don't want x to mean two different things again. So the area between a and x of f of t. assuming that we have a continuous and differentiable function, because if we don't, things kind of break down a little bit. For us, everything's going to be continuous and differentiable. And as we just said, the derivative of this area function is f of x. So what we're doing here is we are finding the derivative of an antiderivative, effectively. And we'll see kind of how these merge together. So for example, we want to find the derivative of this area function for t cubed plus 4t dt, and then find the derivative for the area function going between 0 and x of e to the minus t squared. Well, so these are actually really, really easy ones to solve. You just need to make sure that you get it into this form. So sometimes what we would do on maybe a test is we would write this as the area function from x to minus 7 of, in this case, t cubed plus 4t. We'd said before that you can flip the bounds on this area by putting a minus sign out in front. So you just put a minus sign out in front and then get the minus 7 down below, the x up top. And doing that, we just take the function that we have on the inside and evaluate it at x. So doing so, we get the t cubed plus 4t. We just replace the t's with x's, get x cubed plus 4x. And then for the second example, same thing. We get e to the minus x squared. Okay, so we had a fundamental theorem of calculus part 1. We also have a fundamental theorem of calculus part 2. And this is going to relate derivatives and antiderivatives kind of nicely, or antiderivatives and areas under curves. So far what we've said is that this expression going from a to b, so the expression we have on the left, it's the net area underneath f of x going from a to b. And if you take capital F to be an antiderivative for little f, and it's any antiderivative, and I'll explain why in just a moment, the net area between a and b for little f of x is capital F at b minus capital F at a. Okay, now the reason why you can take any antiderivative is because regardless of what constant you pick, when you take the f of b and you put some constant in there, you'll get your plus c from the f of b, but then you'll get a minus your plus c in the f of a. So you can nicely just take your plus c part to be 0. And when doing what we'll call definite integrals, so these kinds of problems, you don't even have to worry about the plus c. And then notationally what we could do is we could say that capital F of b minus capital F of a, it's just capital F of x evaluated at x equals a and x equals b. So that's just what this vertical bar means. Okay, so we'll do a couple of straightforward examples, some ones we've kind of seen, and then I'll do kind of one more complicated one to wrap up. So the first one that we want to do is we want to find the definite integral from 0 to 3 pi of sine of x dx. Okay, so we need to come up with an antiderivative for sine of x. Antiderivative for sine of x is minus cosine plus c, but as I'd said, for doing definite integrals, the plus c doesn't matter, so we'll just take it to be 0. So we'll go and take minus cosine of x and evaluate it at 3 pi, and then subtract off minus cosine of x evaluated at 0. When we do that, we get minus cosine of 3 pi minus minus cosine of 0, and when we take care of the minus signs, we get 2. Okay, so then we could go and find the area from minus 1 to 6 of 2x minus 6. So that was the first geometric example that we had. So that was the one where we had a triangle with some negative area, and then we had a triangle with some positive area. What we'll see here, we want to come up with an antiderivative for 2x minus 6. So x squared minus 6x will do. We'll then evaluate it at 6 and subtract off this expression evaluated at 1. When we do that, we get 6 squared minus 6 times 6 minus 1 squared minus 6, which is 0 minus minus 5, for 5, which was incidentally the area that we found before. Okay, now we'll go and take that trapezoid example that we just had. So find the area between 2 and 4 of 2x plus 3. An antiderivative will be x squared plus 3x. We'll evaluate our antiderivative at 4 and 2. So we'll get 16 plus 12, which is 28, minus 2 squared plus 3 times 2, which is minus 10. We add up those two values, and we get 18, which is the value that we've had at this point a couple of times. And then lastly, we could go about finding the area between minus 1 and 2 of x cubed. We'd previously found it to be 15/4, and conveniently that's what we get. So we'll go and take an antiderivative for x cubed. X to the 4 over 4 will do. We'll then evaluate it at 2 and get 4, and then subtract off x to the 4 over 4 evaluated at 1, so subtract off a fourth, get 15 over 4. Okay, so then I want to do one kind of concluding example, and this is something that showed up on, I think it was a test a couple of years ago. So looking at this, it looks kind of strange, and maybe it's not obvious what we'd want to do with this. So we want to find the derivative with respect to x of the integral from 0 to cosine of x of t to the 4 plus 6 dt. So I'm going to do this in two ways. First, I'm going to do this with the fundamental theorem of calculus part 2, and then I'm going to do it with the fundamental theorem of calculus part 1. So the first thing that we could do is we could say, well, we could go about finding the definite integral. We know how to do that at this point. It's not too bad. So we find an antiderivative for t to the 4 plus 6. So we get t to the 5 over 5 plus 6t. We evaluate this at cosine of x and 0. When we do that, we get cosine to the 5 over 5 plus 6 cosine of x. So that deals with the definite integral part of this expression. And then the second part of what we need to do here was find the derivative with respect to x. So in other words, find the derivative with respect to x of cosine to the 5 over 5 plus 6 cosine. Well, that's easy enough. We know how to do that. That's just finding a derivative. We've done this hundreds of times or so at this point. And we get cosine to the 4 times minus sine of x from our chain rule, minus 6 sine of x. Okay, so that's one way that we could go and do this. The second way is we could go and do fundamental theorem of calculus part 2. So we could go and find the derivative with respect to x of the definite integral 0 to x of t to the 4 plus 6t dt. That's easy. We know how to do that. Fundamental theorem of calculus part 1. Likewise, we also know how to find the derivative of cosine of x. So let's go and define the function f of x to be just the area function going from 0 to x of t to the 4 plus 6 dt. The other thing that I'll say that I haven't said so far is that you have to include this value at the end. Well, actually, I probably said that when we were talking about antiderivatives. So just remember, you have to include the variable you're integrating over. For us, there's only ever going to be one variable. When you get off to Calc 3, there could be two or more. There it becomes really, really important. Here, it's just good notation. Another way to put it is that this expression for the area is saying you're going to sum up an infinite number of rectangles with height t to the 4 plus 6 and width dt. So in effect, what this is saying is the dt is representing the width of your rectangles. So again, if you didn't include that, it would say you're summing up the areas of rectangles that have no width. So just for good notation, make sure you include the dt or the dx or whatever you're integrating over. Okay, so we have the f of x defined as so, and then we'll define g of x to be cosine of x. So now what we're doing is we're saying, well, this integral from 0 to cosine of x of t to the 4 plus 6t dt, that's just f of g of x, so just a function composition. And then we're asking to find the derivative of this function composition. So this is just a straight chain rule, and it's something that we've done again about 100 times or so at this point. So when we do that, we could easily find that f prime from fundamental theorem of calculus part 1 is going to be x to the 4 plus 6, and g prime is going to be minus sine of x. Okay, so then we have our chain rule. So our derivative with respect to x of f of g of x is going to be f prime evaluated at g times g prime. So we get g to the 4 plus 6 times minus sine, and evaluating at g, we get that our derivative of f of g of x is going to be cosine to the 4 of x plus 6 times minus sine of x, which was incidentally exactly what we had here, just factoring the minus 6 out. Okay, so I think that says about everything that we need to say here about areas under curves. As I said, the next video will be kind of shorter and it's just going to wrap up a couple of ideas with areas under curves, tie a couple of ideas together, and then that'll be the end of the material that we need to cover for Calc 1. And I will see you all then.